House allocation problem. The house allocation problem is a model for understanding the allocation of indivisible goods. It involves a set n of n agents, each owning a unique house, and a strict preference ordering over all n houses. The objective is to reallocate the houses among the agents in an appropriate way. A modern version of the same would replace houses by kidneys. While any possible strict preference ordering over the homes is permitted, the set of preferences over all allocations is restricted. In particular, an agent is different between all allocations that give her the same house. Therefore, the Gibbard-Satterwhite theorem does not apply in this setting. One could select an allocation of homes in a variety of ways, perhaps so as to optimize some function of the preferences and then investigate if the resulting allocation rule is strategy-proof. However, this ignores an important feature not present in earlier examples. In this environment, agents control the resources to be allocated. Therefore, an allocation can be subverted by a subset of agents who might choose to break away and trade among themselves. For this reason, it is natural to focus on allocations that are invulnerable to agents opting out. Number each house by the number of the agent who owns that house. An allocation is an n vector A whose ith component AI is the number of the house assigned to agent I. If A is the initial allocation, then AI equals to I. For an allocation to be feasible, requires that AI not equals to AJ for all I not equals to J. The preference ordering of an agent I will be denoted greater than in I, and X greater than in I to Y will mean that agent I ranks house X above house Y, denoted by A the set of all feasible allocations. For every S which is a subset equals to N, let A of S equals to the set of Z in A such that Zi in S for all I in S. Denote the set of allocations that can be achieved by the agents in S trading among themselves alone. Given an allocation A in A, little a in capital A, the set S of agents is called a blocking coalition. For A, if there exists a Z in A of S such that for all I in S, either Zi is greater than in I to AI or Zi equals to AI, and for at least one J in S, we have that Zj is greater than in J, AJ. The blocking coalition can, by trading among themselves, receive homes that each strictly prefers or is equivalent to the home she receives under A, with at least one agent being strictly better off. The set of allocations that is not blocked by any subset of agents is called the core. The reader will be introduced to the notion of the core in Chapter 15, Section 15.2, where it will be defined for a cooperative game in which utility is transferable via money, a TU game. The house allocation problem we consider is an example of a cooperative game with a non-transferable utility, an NTU game. The definition of the core offered here is the natural modification of the notion of TU core to the present setting. The theorem below shows the core to be non-empty. The proof is by construction using the top trading cycle algorithm, TTCA. Definition 10.5 Top trading cycle algorithm. Construct a directed graph using one vertex for each agent. If house J is agent I's kth ranked choice, insert a directed H from I to J and color the H with color K. And H of the form II will be called a loop. First, identify all directed cycles and loops consisting only of ages color 1. The stricter preference ordering implies that the set of such cycles and loops is node disjoint. Let N1 be the set of vertices agents incident to these cycles. Each cycle implies a sequence of swaps. For example, suppose I1 point to I2 point to I3 point to and so on point to IR is one such cycle. Give house I1 to agent IR, house IR to agent IR-1, and so on. After all such swaps are performed, delete all ages colored 1. Repeat with the ages colored 2 and call the corresponding set of vertices incident to these ages N2 and so on. The TTCA yields the resulting matching. This algorithm is used to prove the following result. Theorem 10.6. The core of the hash allocation problem consists of exactly one matching. We prove that if a matching is in the core, it must be the one returned by the TTCA. Under the TTCA, each agent in N1 receives his favorite house, i.e. the house ranked first in his preference ordering. Therefore, N1 would form a blocking collision to any allocation that does not assign to all of various agents the houses they would receive under the TTCA. That is, any core allocation must assign N1 to houses just as the TTCA assigns them. Given this fact, the same argument applies to N2. Under the TTCA, each agent in N2 receives his favorite house, not including those houses originally endowed by agents in N1. Therefore, if an allocation is in the core and the agents in N1 are assigned each other's houses, then agents in N2 must receive the same houses they receive under the TTCA. Continuing the argument for each NK proves that if an allocation is in the core, then it is the one determined by the TTCA. This proves that there is at most one core allocation. To prove that the TTCA allocation is in the core, it remains to be shown that there is no other blocking coalition S, which is a subset equals to N. This is left to the reader. To apply the TTCA, one must know the preferences of agents over homes. Do they have an incentive to truthfully report these? To give a strongly positive answer to this question, we first associate the TTCA with its corresponding direct revelation mechanism. Define the top trading cycle TTC mechanism to be the function mechanism that, for each profile of preferences, returns the allocation computed by the TTCA. Theorem 10.7, the TTC mechanism is strategy proof. Prove let pi be a profile of preference ordering and A the allocation returned by TTCA when applied to pi. Suppose that agent J in NK for some K misreports her preference ordering. Denote by pi prime the new profile of preference ordering. Let A prime the allocation returned by TTCA when applied to pi prime. If the TTCA is not strategy proof, AI prime is greater than AI in I's preference. Observe that AI equals to AI prime for all I which is in the union of n R with index R starting from 1 to k minus 1. Therefore, AI prime is in n minus the set of the unions of n R with index R starting from 1 to k minus 1. However, The TDCA chooses AI to be agent I's top-ranked choice from N. Remove the set of NR, the set of unions of NR with index R starting from 1 to k minus 1, contradicting the fact that AI prime is greater than AI in I's preference. If we relaxed the requirement that preferences be strict, what we had previously called a blocking set is now called a weakly blocking set. What we had previously called the core is now called a strict core. With a difference, a blocking set S is one where all agents in S are strictly better off by trading among themselves. Note the requirement that all agents be strictly better off. A core is the set of allocations not blocked by any set S. When preferences are strict, every minimal weakly blocking set is a blocking set. To see this, fix a weakly blocking set S. An agent in S who is not made strictly better off by trade among agents in S must have been assigned their own home. Remove them from S. Repeat. The remaining agents must all be allocated houses that make them strictly better off. Hence, when preferences are strict, the core and the strict core coincide. With indifference permitted, the strict core can be different from the core. In fact, there are examples where the strict core is empty and others where it is not unique. Deciding emptiness of the strict core is polynomial in the size of n. Another possible extension of the model is to endow the agents with more than one good. For example, a home and a car. Clearly, if preferences over pairs of goods are sufficiently rich, the core can be empty. It turns out that even under very severe restrictions, the core can still be empty. For example, when preferences are separable, i.e. one's ranking over homes does not depend on which car one has.